Welcome to the session of vibration engineering. In this session, we will try to understand what is a dynamic vibration absorber. We also call it a passive vibration absorber. I will start with the basic operation of a vibration absorber, and then we will see the mathematical part of a dynamic vibration absorber. To understand the function of a vibration absorber, let's consider a problem of a pump mounted on a platform. The pump is rotating with certain rotational speed, and because of the unbalance in the forces, a force is acting on the platform. The platform is having stiffness K in the vertical direction, and the force acting on the system is denoted by F0 cos omega Ft, where F is the excitation frequency. I am assuming m is the mass of the pump and the K is the stiffness, so I can say that the total stiffness may be 2K. When I will calculate the response of this system using the force vibration philosophy, I am getting that the response is coming of a significant amplitude. Now, if I want to reduce the vibration of this system, I can use a dynamic vibration absorber, and the philosophy of vibration absorber is that we have to add an additional spring mass system on our parent system. So now let's assume a secondary spring mass system of stiffness K and mass M, and the basic requirement for the vibration absorber is that the natural frequency of vibration absorber should equal to the excitation frequency. Here omega is the excitation frequency of the pump. Let's the pump is exciting with a 50 Hz value, then this natural frequency of this vibration absorber should be 50 Hz. So, and the next job is to add the vibration absorber on the actual body. So when I will add this vibration absorber to the main system, I will observe that the response is now reduced significantly, and now the mass M is vibrating with very large amplitude. Please understand that I have considered a system, then I have added a second system to the system, assuming that the natural frequency of this second system is matching with the excitation frequency. When I will add the secondary system, I will observe that the primary system will now vibrate with very less amplitude, and the secondary system is vibrating with a higher amplitude. So we can also see the same use of vibration absorber for a multi-story building. Let's assume that we are having a multi-story building, and here I have made the mathematical model of this multi-story building, and I am showing three different modes of multi-story building corresponding to frequency F1, F2 and F3. Since F1 corresponding to the first mode, it will be lower than other two values, and now I want to add a vibration absorber corresponding to the first modal frequency. So what I need to do, I have to design a vibration absorber whose natural frequency should match with the first mode frequency. So I will make a vibration absorber using K1 by M1 of equal to the F1 value, and I will add the vibration absorber at the top mass. I can also use a different type of vibration absorber. Instead of using a spring mass system, I can use a beam with a mass M. Both will have equal effect, and when the actual building will vibrate, absorber will absorb the vibration of the building, and vibration of the building will reduce and vibration of absorber will be high. Now if I want to use a vibration absorber corresponding to second mode frequency, please understand that a single set of vibration absorber work for a particular frequency. We cannot use a single absorber for two different frequencies because it is having a unique natural frequency. So if I want to design the vibration absorber for second mode, I can use a second system having M2 and K2, and the K2 by M2 square root will be equal to the second natural frequency. Now you can see here that in the first case, when I was trying to reduce the vibration of the first mode, I have added a vibration absorber at the top mass, but here I am adding it at the second mass. Why? Because the vibration absorber work effectively when it will adhere to a point of maximum displacement. We can see here that in the first mode the top mass is moving with the large amplitude. In the second mode I am considering that the second mass is moving with the large amplitude, and similarly if I want to add a vibration absorber for the third mode, I can assume that this mass is moving with the larger amplitude, and for this purpose when I will design a vibration absorber for the third mode, I will preferably add my vibration absorber on the third mass, and the natural frequency of this third vibration absorber will be equal to the F3. Now to understand the mathematical part of vibration absorber, let's start with the force vibration response of a 2 degree of freedom system, because the basic philosophy of vibration absorber is based on the response characteristic of a 2 degree of freedom system. And for this purpose let's consider a 2 degree of freedom problem. Here I have considered a 2 degree of freedom system having 3 spring elements and 2 masses. I am applying a harmonic force on the first mass, and the magnitude of harmonic force is F0 cos omega Ft. When I will write the equation of motion for this system, this will be my first equation where I am having force on the right hand side. This is my second equation. As I am not having any force on the second mass, the right hand side for this equation will be 0. When I will add the general solution into my governing equation, I will get the response of the system. Here I am not going through the mathematics of the response, I am directly writing the formula for the response. So when I will put the general solution into my governing equation, I will get these two response equation. In the first equation is corresponding to the response of the first mass. Here we can see that the F0 is coming in the numerator, and the K2 plus K3 omega F square and M2 omega is the excitation frequency. Similarly, here is the response for the second mass. If I can see here that the response is a function of the excitation frequency as well as the other component. So if I will make a plot between the response and the ratio of the two frequency mean the first natural frequency, or I can use the second natural frequency. Here I am plotting the response corresponding to the ratio of omega f by omega 1. Omega 1 is the first natural frequency or first eigen frequency which I can calculate using the eigenvalue formulation. So now when I will see the response characteristic, I can see that as the excitation frequency is increasing, because the natural frequency of the system will be a constant and I am changing the excitation frequency, so as the excitation frequency will increase and when it will match to the natural frequencies, therefore the ratio will become 1. I will be having a large amplitude vibration of the first mass. Here the solid line is corresponding to the first mass. When I will increase the frequency further, my formula will give me a negative value, but again it will be a very close to the infinite. So I am writing plotting my line from the negative infinite, and as the frequency will increase, the response will become 0 at certain value. This certain value will be corresponding to a particular value of excitation frequency, and again it will increase and go to the positive infinite direction. And when it will go further, again it will start from the negative infinite direction and it will go in this way. Similarly, when I will see the response of the second mass, I am having the similar pattern, but I can see here that for the second mass, initially it will go to the infinite value. When it will go further, it will start from the negative value. When the first one will reaches to 0, it will also be very close to the 0, but after that the response will go again to the negative infinite direction, and further it will come from the positive to the negative. I would suggest that you should not bother that how these lines are going, because when you will put the value of excitation frequency, keeping all the values a fixed value, you will find this response. You can use any computer program to plot the response of first mass corresponding to the excitation frequency. Similarly, you can plot for the second mass. And if I will consider only the absolute value, the response will looks like in this fashion, that when I will increase the excitation frequency, the response will increase since we don't have any damping, ideally it will go to the infinite value when the natural frequency is when the excitation frequency is matching with the first natural frequency. When the frequency go beyond, again the response will come close to the zero, and again it will increase to the infinite value, and again it will come back to the zero. And the second peak we'll observe when the excitation frequency will be close to the second natural frequency of the system. So now what is the significance of this curve? This curve basically indicates that if I will be having a point where the response of the two masses is very close to the zero, then we should use this philosophy to develop a system which can reduce the vibration of a system. So using this idea, we have developed a concept of vibration absorber, and we can understand the concept of vibration absorber using a simple example. I am having a single degree of freedom system of stiffness K1 and mass M1, and I am applying a harmonic force to my system of magnitude F0 cos omega Ft. Omega F is the excitation frequency, and if I will assume that the excitation frequency is very close to the natural frequency of my system, I will be having resonance, or the vibration level of the mass will be very high. And now if I want to design a vibration absorber to reduce the vibration of parent system when it is exciting at omega F frequency, I will consider a second system of stiffness K2 and M2, and the natural frequency of this system will be defined by square root of K2 by M2. Now I don't know what is the value of K2 and what should be the value of M2, but as my intention is that when I will add the secondary system to the primary system, the response of the primary system should become 0 or close to the 0. So now at this point I don't know what will be the value of the second system. I am just considering a second system, adding it to the primary system. The primary system is having a force, and now my system has become a 2 degree of freedom system. So when I will calculate the response of my system, I will be using these two formula, that this is the response for the first mass and this will be the response of the second mass. This formula is same way as we have calculated in the previous lecture of when we have calculated the force vibration. Now as my intention is to reduce the vibration of the first mass, I will consider this x1 will be 0 in this equation, and when I will put x1 will be 0 in this equation, I will be observed that this term will become 0 and this will be equal to the 0, and which will give me that the omega f will be equal to square root of K2 by M2 is equal to the natural frequency of the secondary system. So from this mathematical derivation we can observe that if I am having a secondary system whose natural frequency is matching with the excitation frequency, response of my parent system will become 0. We can also understand this by taking a numerical problem.